me share the screen. All right. So last time we stopped here, where we talked about how the maximum rate of climb for a helicopter changes with speed, because with speed, my extra power that is available also changes. And it's also a function of your the takeoff weight at which you are flying, and also the altitude at which you are operating. Because what happens with altitude, my power required will also change, and power available may also change. Now we look at the concept of range endurance. Rate of climb we've already seen, so we look at now range and endurance and maximum speed actually here. So range endurance and maximum speed. So last class I showed you how using the formula we have derived earlier and using some code, we could plot different components of total power and finally also plot the total power. So you can see anywhere, I mean, the power available, assuming that your height is not changing and you are doing steady level flight, your power available would be constant and the power required would vary like this power bucket. So we call this graph as power bucket for helicopters. So now, based on this, we can identify and also derive and obtain expressions for speeds corresponding to best endurance, speed corresponding to best range, and the maximum level flight speed possible. So maximum level flight speed is quite straightforward. You can see it here. Wherever your power available actually matches the power required, that becomes your limit. It's called maximum level flight speed or never exceed limit speed or whatever. Some people also call it never exceed speed. Okay. So that is easy to get as long as you know the power available graph from the engine and stuff. Other two things, best endurance. So endurance is a function of what? It is function of what? What physical parameter of a helicopter is it a function of? Who can answer this? Speaker, you want to say anything about that? Are you getting my question? Are you there, speaker? Hi,
sir.
Yeah.
Sir, yes, sir.
Yeah. So my question, I mean, you heard my question.
Sir, can you repeat it once again, sir?
The question is, what factor does endurance of the helicopter depend on? What physical characteristics or parameters are going to determine the endurance of a helicopter?
Okay. Power loading, sir. Like for hour, how much?
No, I'm talking about any condition at any point. I mean, if I just hover at any point of time, say, what parameter governs the endurance of any aerial vehicle, even if I leave helicopter? Endurance is directly a function of what? Which parameter? Which physical characteristic of an aerial vehicle? Who can answer?
Sir,
yes,
efficiency.
Efficiency is with respect to something, right? Efficiency can help you increase or decrease endurance, but it will not determine your endurance. So Anil has said fuel. Yes, the fuel volume is important, absolutely, because depending on the fuel volume, we will determine, I mean, what endurance you're going to achieve. And what else?
The weight of the
Time of flight.
Drag.
Altitude at which it is flying. So Nikit has said it is altitude. So what does altitude govern actually?
Sir, density.
Density. And what will density govern actually? What is it going
It's
to affect?
fuel efficiency. So how
Of
fast
what?
or slow the
Fuel
fuel
efficiency
will
of
burn.
what? Fuel efficiency of what?
Engine.
Combustion.
For the engine.
Engine's fuel efficiency.
Yes.
And what is the term actually used for the engine fuel efficiency? What is the technical term? How do you
Sir,
represent the
SFC.
Specific fuel consumption.
Exactly. So I was hoping somebody would say that. Yeah. So specific fuel consumption, right? So most of the engines which helicopters use are turboshaft engines. So there you talk about SFC. They are all shaft-based engines. They are not thrust-based engines. So specific fuel consumption is actually power-based specific fuel consumption. So we would talk about, I mean, how much of unit of fuel in terms of kilograms of fuel would be consumed for every unit of power every hour. So in that sense, I mean, one can define SFC. So now next question is, what does SFC depend on?
quality of fuel, sir.
Calorific value of fuel.
Quality of fuel, sir.
Quality of fuel? No.
And oxygen.
No, I mean, you are going into combustion, right? I mean, I'm not concerned about what is happening inside the engine. I am worried about, I mean, what parameter of what physical characteristic or physical aspect of my helicopter is going to determine, I mean, how much fuel I'm going to consume. My helicopter design here, I'm not talking about change in design. I have given you a helicopter. Now, what factors it's going to tell how much fuel you're going to consume?
Sir, mass flow rate of air.
Where? From where?
Mass flow rate.
Yeah, from where? Whose mass flow rate you're talking about?
Incoming air.
Rotor, you're saying you're talking about engine. I am not getting it actually.
Yeah,
Through
through rotor.
I mean, you guys are going too much into nitpicking. I mean, it cannot just be function of mass flow rate. We are not talking about hovering flight or axial flight, right?
Sir, the compressor efficiency. I mean, how
And
much
who is
air is compressed?
compressor here? Yeah. It is simply dependent on the power it is consuming, and power is dependent on the thrust it is actually producing. So how much I am lifting, that is going to determine how much fuel I'm going to consume. It's very simple. I did not ask any trick question. Okay, so all I was expecting is that, yes, SFC, that was the correct thing. And SFC depends directly on your power. So if I want to minimize my SFC, I have to minimize my power. So I can minimize my power either by reducing my weight or choosing a speed. Now, reducing a weight may not be a choice for you. Why? Because I have to fly a mission. My goal is to lift certain weight. I cannot say that, I mean, I'm going to reduce my payload to minimize my power consumption. So only way I can actually look at varying my power consumption is by changing the speed for the helicopter. And that's where the power bucket comes in. So my SFC is going to be minimum and my power is going to be minimum. Okay. And that you can all see will happen at the point where your power is minimum. So this is the point where we also get maximum rate of climb. I'll also actually get maximum endurance. No problem, they're fine. So,
Sir,
yeah,
for a given mass flow rate, if power is minimum, then we can have a
what about
maximum.
who is talking
maximum
about mass? Why are you so obsessed with mass flow rate, and whose mass flow rate?
Incoming air into the compressor. We are
Engine-
talking.
Incoming
Yeah.
flow through engine is not your concern at all. Engine is supposed to deliver certain amount of power. So why are you bothered about, I mean, what happens to the compressor, what happens to the turbine, how my combustion process is? Engine's parameter is out of question. I mean, engine's efficiency may change slightly depending on the power you're trying to extract. But all the engines are designed to deliver a range of power, and their efficiency is not going to change dramatically in that range of power. So engine is out of question here. You are not going to change engine for a helicopter, right? You are already flying with a given engine. So that is not going to change dramatically. The fuel consumption is only going to change based on what altitude you are flying at, and actually everything is finally dependent on your power, because power changes with other things. So bottom line being that my velocity for best endurance corresponds to the point where my power is minimum, and it's the same thing which is true for fixed wing airplanes also. If I take a fixed wing airplane and draw the power graph for that, it comes out to be something like this. Okay. For a propeller driven airplane or a jet airplane or something. Okay. And here also we do the same thing. We say, oh, okay, look, this point has the minimum power, and therefore this velocity would be my velocity for best endurance, VBE, which I have denoted here with mu x. So this is actually mu BE. I can call this as mu BE, best endurance speed. And the range. Now the max range depends on what factor? What determines the maximum range?
Drag.
Not one thing. No. Not just drag alone. It is same as, I mean, for airplanes also.
L by D ratio.
Exactly, L by D ratio, yes. So what is L by D ratio known as? There is another name for that.
Aerodynamic efficiency.
Propulsive efficiency, yes. So it's propulsive efficiency which actually determines your maximum range. Why? Because, well, when my power is minimum, I can ensure that I can keep flying for longest. But that doesn't ensure that, I mean, I'll be able to achieve the highest range. So if you look at that, okay, power to velocity ratio is also same as the lift to drag ratio. How? Because for helicopters, your power can be approximated with thrust into velocity and divided by velocity. So actually, I think this is not a right analogy. I mean, I'll derive this later. Okay. Fine. Get rid of this. Yeah. So propulsive efficiency is actually practically it's the slope of power to velocity graph. Okay. So CP2, I mean, this graph is actually not, I would say, very sensibly drawn. It's more of a representative graph because I have one direction or one place. I mean, y-axis is a dimensional power, and here I have mu. So what I will have is I will either have power versus velocity diagram, or I'll have CP versus mu diagram. Okay. What is already here. So assume this is a CP versus mu diagram because I have not put any numbers on that. So for CP versus mu diagram, I can draw a tangent to this power graph from here. Okay. When it is plotted at the true scale. And this tangent would actually give me the propulsive efficiency. And that's what actually gives me the best range. So this is the speed which will fetch me the best range. And other I have already seen that yes, the point where my power available and power required meet, that gives me the max level flight speed. So now this is qualitative thing, that is how you can obtain these numbers graphically. But then, I mean, because we already have equation for this particular equation in some form, I can try to calculate this analytically. So let's do that. All right, so coming down here, if my endurance can be maximized with minimum fuel burn, that is lowest power required. And fuel burn, which is basically SFC, would be lowest when my power required is lowest. So the SFC versus advanced ratio graph would follow the CP versus mu graph. Okay, so my fuel consumption is going to follow exactly the same trend as my power consumption graph. And therefore, if I want to minimize my fuel consumption to maximize my endurance, I must minimize my power consumption. So I need to find out the speed at which my power consumption will be minimum. But now this expression that we have here, the whole equation, that I have, which you can see clearly here, is somewhat complicated. If I directly try to differentiate it with respect to mu and try to solve it, I may end up getting somewhat complicated equation. So because we are doing analytical things, so we can simplify the problem somewhat. And there is evidence that we can do that. So what happens, I mean, when the kind of speeds we look at for best endurance scenario, my profile power is not very high enough up to that point. So what we'll do is that we'll say, okay, the contribution for profile power may not be very high at this best endurance flight condition. Let me ignore this to make my life easier. I'm not saying that I'm in normal scenario, I'll do this, but only for analytical purpose, I am actually making this kind of assumption. And of course, there is no climb here. So if I'm just doing steady level flight, so I'll only be left with these two terms. So the claim we are making is that near this best endurance speed, mu x, my profile power is small, and therefore the rate of change of this profile power will be even smaller. So when I take dCp by d mu, I can happily ignore this particular term, because it will be small. So now minimum power is essentially determined by.
Sir, can you repeat this formula, sir? There is mu cube twice, sir. Is it intentional?
What is twice?
In the formula mu
Oh
cube.
yeah, no, that is a mistake actually. That's a typographic mistake.
And sir, there is CT square
Q1
also.
mu cube, and this is not correct. And this is mu CT square. By 2 mu. So what is the normal formula? Same formula. Okay, I mean, just there's a typographic mistake when I note it down. So when I write it, I mean, I write it right, but I mean, the notes will come out with the incorrect manner. All right. So now with that assumption that my profile power contribution and the derivative profile power contribution is very small, I go to the simplified expression purely for this particular purpose of getting analytical expression. So now my CP is approximated to kappa C W square by 2 mu plus half F over A mu cube. So for a minimum for this particular function, to achieve a minima, I take the derivative dCp by d mu and set it to 0. So dCp by d mu equals to minus of kappa CW square by 2 mu square plus 3 by 2 F over A mu square, and kappa CW square by 2 mu square equal to 3 by 2 F over A mu square. So now, I mean, we see this gives me a nice and clean expression in terms of mu to the power 4, and using this particular expression, mu x comes out to be kappa CW square by 3 of F over A, and the entire thing is raised to the power 1 by 4. Okay, because this, as you can see, this gives me mu to the power 4 equals to 1 by 3 kappa CW square by F over A. Okay, so that's what we end up getting. So it comes out to be this guy mu x. So this is my approximate formula for velocity, or rather in this case mu, for best endurance, which I'm denoting using mu x. So this is the condition for best endurance.
Sir, what is CW?
You tell me what is CW. We have already talked about that.
Sir, minimum coefficient of power.
No. Why would coefficient of power be there inside the formula for power, or the formula for power coefficient? What is this formula? Who will tell what is CW? Sachindra.
Trust.
Why thrust?
No, sir. I was saying, but then you asked for some other guys' name.
No, so tell what you were saying. CW is
thrust coefficient, and at hover it is thrust is equal to
but
weight.
this is not hover. Right, there is forward flight, right? We are talking about. What is the value of thrust in forward flight? That's my helicopter in forward flight. What will be its thrust equal to?
Wait,
Well, approximately equal to weight, because the thrust has to also provide forward propulsion. This is alpha, right? That's what you are calling homework assignment 1. Different shaft angles, how much helicopter is tilted by. So we can say T cos alpha equal to W, but this cos alpha is a small angle, 3-4 degrees max typically. So I can approximate very happily as T equal to W. So my CT becomes equal to, sorry, CW, and that's what we are using. So it's a weight coefficient. Okay. Fine. So that is my derivation for speed for best endurance, or advanced ratio for best endurance. Now, if I want to convert this to actual speed, dimensional speed, you can simply multiply this with omega r. Okay. And that will give you the approximate forward speed for this best endurance scenario. Now I can do some more little bit of juggling with this expression that we have obtained. Nothing very fancy. So this is what I have. Now I can actually, try to replace this with some other parameters, such as lambda h. For example, if you have information about lambda h, I know that for sure that lambda h square equals to CW by 2. So if I plug that in here, it will become lambda h to the power 4. So lambda h would actually come outside. So another expression for mu x could be lambda h into 4k by 3f by a to the power 1 by 4. And or you can write it like this, square root of CW by 2. Or finally, in the dimensional form, I can write as Vx equals to square root of W by 2 rho a into 4 times kappa by 3 times f over a to the power 1 by 4. So this is the dimensional expression for the velocity for or speed for best endurance. Oh, by the way, before I forget, the exam will be proctored. Okay, I will send out links to all of you. We'll create, how many people are there? Around 14, 15 people are there. So we'll create 2 Zoom links over which we'll conduct the exam, and everybody will have to have their videos on, and you have to place your camera in such a way that one can see your hands and so on. Also, this will be an open notes exam. You are allowed to keep with you any notes that you have prepared so far. You can even prepare your own cheat sheets, which could be collection of relevant formulas, which would be relevant and important for you. Don't try to bring your handwritten full notebook, because if you keep turning pages, we have limited time. You'll run out of time if you're busy only trying to find the correct formula. So keep that also in mind. So you're not supposed to remember or memorize anything. I don't believe in memorizing stuff. I believe in acquiring knowledge and using it whenever you need it. So therefore, you can bring in as many handwritten notes, but no printed material is allowed. You cannot bring printed materials or Xerox material from other people. Should be your own handwriting, your own material. And as part of the exam process, you can submit that also as a separate file. That whatever you are bringing as a cheat sheet, I may probably give few marks for that also. So you may have a couple of marks on preparing a nice cheat sheet for your exam, because preparing cheat sheets is also a good skill. I was really good at it actually, because most of my exams in Maryland were all open book, open notes exams. So I used to prepare really nice cheat sheets in few pages. So I would never have to waste my time searching for a particular formula which I don't remember. So keep all this thing in mind. This is general information for you for the exam, so that you are prepared for that. I have already sent you the sample exam paper. So make sure you solve it. It will give you good practice for your midterm exam. All right. And if you have any other query, feel free to ask now or before the exam. Okay. So let's come back. All right. So this is what we have for endurance. Now let us move on to what we can do. So this gives you a good estimate of Vx, and if you actually do it for a representative helicopter, you go ahead and find these things out. You will find that the typical best endurance speed for a large helicopter would be 110 to 150 km per hour. I can tell you for my small helicopter, that unmanned helicopter which we are now selling, that unmanned helicopter, the best endurance speed is around 60 km per hour, which is still much better than a typical multi-rotor. Multi-rotors maxes out at 60 km per hour. It will be like, highest power condition. And they are okay around 30 to 40 km per hour, more or less. But helicopter can easily go to 100 km per hour also. And yeah, so that's the thing. In knots, it is 60 to 80 knots for full scale helicopter. And in terms of speed, it is 110 to 150 km per hour. Let us see what is my best range speed. Now, range is maximum distance the helicopter can fly based on given takeoff weight, fuel plus payload, and the prevailing atmospheric conditions. So I have to fly the max distance with a given tank of fuel under prevailing circumstances. So best range corresponds to max propulsion efficiency or minimum power to velocity ratio. Okay, that is the point where my power consumption is minimum for the given velocity, and therefore this P to V ratio. So I want to look at the slope of my power graph at all the points and see where do I get minimum slope, and that's why you take the tangent to the line. So we saw that in the power graph that we had. Yeah, really bad. Okay. Right. So you can see at every point I can actually make a slope, right? I can make slopes at every point. So I try to find out where my slope is going to be minimum, right? Because this is what, if you look at this thing is, this particular angle is P divided by V. And I want this angle to be small as possible. So I have minimized, so this tangent to this line would actually give me minimum P by V, minimum power to velocity ratio. Or in other terms, we actually want to maximize velocity to power ratio. That is, my velocity per unit of power should be maximum. And this thing is same as L by D, okay, lift to drag ratio. So this also corresponds to the maximum L by D ratio of the helicopter, and the same applies to any aerial vehicle, right? Because in forward flight, even my helicopter actually behaves like a airplane with a circular circular wing. So let us see. We now go ahead and try to do the same thing for range. Okay, my range expression is actually not scanned. I think so, yeah. 4.6, 4.7, and then it jumps actually because it was at the back of the paper. So it is not scanned in this thing. Okay, yeah. Let me see if it is there in the next page. It is not there. Okay. So I'll actually derive it. Just let me grab it for a moment. So what we'll do is that we'll again go ahead and make that same kind of assumption. Okay, so now you note it down carefully because it's not there in this. Okay, I mean, I can go to, I can stop sharing this and I'll use the whiteboard here. Okay. So now our objective is to find out the point where I get minimum P by V. That is my objective. And the point where this actually happens would correspond to my velocity for best range, or as I have been calling it, mu y, okay, or even Vy in my derivations. So this corresponds to best range condition. So again, I mean, like the way we said earlier, that was the point where I have minimum power. That point actually my profile power was less, so I ignored the profile power component. So I'll continue doing the same thing here. Although at this point my profile power may still be more than actually induced power, but I simply want to get a nice simple formula. And interestingly, it is not off by so much. So my expression for power Cp equals to kappa Ct square by 2 mu plus my parasite power half mu cube F over A. All right. So that's my expression for power, having ignored the expression for profile power. And primarily we are doing it to make our lives easier. Otherwise, I get up with a really complicated equation which would be hard to solve. So if I have computer available, I mean, I can always solve the equation graphically or using a nonlinear solver or some such thing. But because we want to get nice closed form expressions, we do it like this. So now our goal is to minimize P by V. So what I do, I rewrite this as Cp by mu, because that is going to be same as P by V. Okay. So P by V will also be same as the ratio Cp by mu. Okay. So P by V, Cp by mu equals to kappa Ct square by 2 mu square plus half mu square F over A. All right. So that's what I now want to minimize. So I take the derivative of this particular expression or this particular function and not the Cp. If I take derivative of Cp directly, then I end up getting best endurance condition and not best range condition. So I have to minimize Cp by mu. So in the next step, I do d by d mu of Cp by mu, and that would be kappa twice kappa, sorry, kappa Ct square. Is this? Okay, so kappa Ct square minus divided by mu cube, because mu square will give you -2, so -2 and this 2 down, so -2 up and 2 down will cancel, so you'll be left with minus, plus this is straightforward, this will also give you 2, so it will be mu F over A, and this guy should be equal to 0. So now I can easily find the expression for the mu, which gives me this condition, which allows me to meet this condition. So I call this as mu y, or I call this as mu Br, which will be equal to kappa Ct squared F over A. And this entire thing over 1 to the power 4. So that becomes my expression for advanced ratio for best range. Advanced ratio for best range. And now I can also write this in the dimensional form. So I'll squeeze it in here. Vy or VBR equals to square root of W by 2 rho A into 4 times kappa over. Actually, this is not kappa, right? This was K, right? This was no, this is kappa only. Yeah, this is because it's for induced power. Yes, so it's fine. 4 kappa over F over A. This whole rest to the power 1 by 4. And okay, I squeeze some more in here. Okay, the typical value for VBR for full scale helicopters would be 90 to 100 knots, which corresponds to 170 to 185, 190 kilometers per hour. Okay. So for best endurance, it was 110 to 130 kilometers per hour. And for best range, it is around 170 to 185 kilometers per hour. For my small helicopter, I know it is around 70, 75 kilometers per hour for getting best range. All right. Shall I
Sir.
clear?
Sir, why did we minimize P by V ratio? Sir, can you please explain again why the best endurance case and best maximum range are different?
For the
Because
simple
if
reason that the speed. see,
if we have minimum power, sir, generally, then we can obviously go a longer range.
no,
Why
how
not
can you go?
that?
No. You want your speed to be maximum for that given unit of power. Okay. If I want
So, sir,
to
can
go
please repeat?
further away, if I want to travel a distance, right? I want to go from point A to point B, right? Now, the distance S is a function of velocity, right? Because the distance, if my speed is constant, I mean, V into T will give me my distance. I want to maximize my distance traveled. Now, but I have to choose my velocity in such a way that for that given velocity, or rather for my what do I say? How should I put it? Right. So my distance traveled is actually a function of velocity. It's not function of directly power. And but power is actually a function of velocity, right? So I have to choose my velocity in such a way that my power consumed per unit of velocity. So V by P, okay, V velocity per unit of power is going to be smallest. That is, for every unit of power that I'm spending, I am able to get the maximum possible velocity. So therefore, this ratio is more important. If I just look at the minimum power condition, my minimum power condition will only give me maximum time of flight. So this velocity, you can now see, is actually some smaller number compared to this, right? Where this, so my one velocity VBE is here and one VBR is here. So you can clearly see always VBE will be less than VBR. But at the same time, I mean, of course, my time of best endurance will be somewhat better than time for best range. But what I am concerned about is actually the product of these two. Okay, because that's what will give me the distance traveled. So VBE into PBE and VBR into PBR, we have to see which one is going to be more. And it turns out that this guy is actually going to be more. VBR into PBR. And that actually is ensured because, I mean, if you come from the fixed wing derivation world, we already know that the propulsive efficiency is, or the condition for best range is to have maximum L by D. And that for helicopter or even for airplane, the maximum L by D happens when we actually are operating at minimum P by V condition. That is, you have minimum
sir,
P by V, or other way around, I can say maximum V by P. So V over P should be maximum. That is, for every unit of power I am spending, I should have the max possible velocity. So it has
Sir,
not slightly.
sir, do you mean to say that if we are traveling at maximum range point, then overall we consume less power to travel from A to B than if we go at best endurance?
Yeah, absolutely,
Yes.
absolutely. Because
Overall.
here I want to see what is my power consumption per unit of distance traveled,
Okay.
right?
But
Not per unit of time.
so, sir, instantaneously, best endurance may consume less power, but overall, it will consume more power because of the time extra time taken by.
Yes,
For the
yes,
propulsion.
yes.
Thank you,
Because
sir.
the main concern is to get maximum distance, not maximum time. And distance is function of velocity. Therefore, that comes into the whole mix of things. So shall I clear the whole thing? I hope you have noted down the most of the things. Right? Yes, no. Erase or not erase?
Yes, sir. Yes, sir.
Everybody fine? Okay, fine, I'm erasing. Nobody is objecting, so I'm erasing. All right, so that is what was the derivation for. I'll go back to my notes because the other condition, as we discussed already, is the best or rather maximum speed for the helicopter. And for maximum speed for the helicopter, we already know that, yeah, the point where my two lines intersect. Yeah, so the point where it intersects, that particular point will be the point where which corresponds to the maximum speed possible. This point, right? So finding out this is straightforward, and we are not going to find it right now in the, using analytical expression, because this point, I mean, my profile power is also high, parasite power is also very, very high, English power may be low. So getting a simple analytical expression is not easy. And another thing, it is a function of power available. So best way is to find graphically. I mean, you can just draw a graph for power and draw a straight line for your available power, and you get the maximum speed possible. And that I told you already what is typical range for maximum speed. It is around 150, 170, 180 knots is max, never exceed speed for helicopters. Now we'll discuss one interesting concept. Regarding various parameters which affect helicopter design. Or what are the parameters which sort of create some form of aerodynamic limit for a helicopter. So again, it's in the continuation of the same discussion, that is if I once again look at my same power versus velocity, and I want to find out the condition for maximum power. The question is, what are the parameters which are going to determine my maximum possible speed? I mean, here I'm saying it's actually function of power available. But then, I mean, I can always choose the slightly better engine, more efficient engine, more powerful engine, and push the power level to higher value. Can I still fly faster? The answer is what?
Yes.
You can fly faster? Are you sure?
up to a limit, I think, and after
Yeah,
that,
but I mean, see, but you will be surprised to know that helicopters are already operating at the maximum limit. So if I give you a helicopter and say, ki, okay, put a bigger engine, more powerful engine, and start flying faster, you actually won't be able to do that, right? So what are the key factors which actually governs or determines your maximum speed of a helicopter? Some of it is already given here, right? On this notes. Are you able to make out what things we are talking about here? So the most critical parameter which actually compromises your ability to fly forward at a higher speed is what? Which is the most critical parameter?
Stall.
Stall. Which kind of stall? Any other ideas? If not stall, what else? What is the single most critical parameter which will prevent you to fly too fast?
Mach number, sir, of the blade tip.
How?
Sir, in the first lecture, we talked about if the blade tip reaches sonic value, then it can't go any faster. If the maximum velocity of the blade tip reaches the Mach 1 value, near Mach 1 value.
Right. So unlike airplanes, when airplanes are stationary, the tip Mach number for airplane is 0. And the forward speed and the Mach number are exactly matching for a fixed wing airplane. But that is not true for a helicopter. And that's what is shown here. This particular line is actually representing the velocity, how the velocity is encountered by a helicopter rotor at different points. Okay. So if I look at, this is the advancing side, right? So what happens here, my velocity is actually increasing here, ut, and then there is also velocity coming from the other side due to forward speed, and it actually adds up. So what happens, this v equal to omega into r plus, and in hover condition, this omega r is already equal to 0.65 Mach number, right? In hovering condition. Now, the moment I start flying forward, I get additional velocity here, which will add to this ut, right? So now I am only left with a room of 0.15 Mach number before I actually reach the limit that is there for normal efficient subsonic flight. What is the limit for normal subsonic flight? What is the point?
3.
I couldn't hear you. Can you repeat?
0.3.
No. What is the limit for efficient subsonic flight? That is, what is the speed or Mach number at which airplanes fly? Fixed wing airplanes, commercial airplanes. So I've got two answers, 0.8. Do all of you agree? Yes, below transonic, that is correct. Anybody else has any comment? Is there
0.7.
Sorry, what?
0.7.
It's actually 0.7, it's close to 0.8. So normally it is around 0.7, 0.78. So if you go and check the Mach number for Boeing's Airbuses, they would be typically flying at 0.78 to 0.8. These are the typical numbers. Because beyond this, if you try to go any faster than this, you will start experiencing supersonic effects, and you will enter transonic regime, which will be not very good. Your power consumptions will start, you will start experiencing drag divergence. So the same thing happens here. So I only have this small room of 0.15 Mach number. So let us calculate 0.15 is how much? If I do 0.15 into
45 meter per second, approximately
Yes.
40.
So 0.15 into 330. into 3.6, 180 kilometers per hour. So that is all you can do. And I can push it slightly by making my tip of the blade swept. So that may give me some more. So I may be able to reach 200 kilometers per hour or something, or 250 kilometers per hour. Okay. So this is the kind of scenario, right? I mean, I don't have a lot of room to fly very fast. And that is actually hindered by it is primarily hindered by the compressibility effect. So this is my rotor disc, as you can see. So when my blade actually is moving in this direction and I'm flying at already high speeds, such as advance ratio of 0.3637, that kind of range for a full-scale helicopter with a like Black Hawk, and let's say example of Black Hawk. My angle of attack in these regions is going to be small, but my Mach number is very, very high. And therefore my compressibility effects comes into picture. And not only that, if your blade may actually even stall here. Why? Because at such kind of supersonic conditions, normally we talk about how NACA 0012 actually has a stall angle of 12 degrees, 13 degrees, something like that, right? But when I go to this kind of high Mach number, 0.8, this same airfoil will actually stall at 6 or 7 degrees. Okay. So this is a very, very low angle of attack, and even then my airfoil may stall. So all those creates problem, and even at this kind of Mach number, the flow on the airfoil may sometimes become supersonic at some places. So it may be subsonic here, but it may become supersonic here, and you may find some small weak shocks sitting here. Okay, most of because I mean it accelerates from here to here, right? Because its airfoil is like that, so it will reach Mach 1 here. So that all those things creates drag, creates pitching moment, creates all kinds of trouble. So that is one clear challenge, that advancing blade compressibility effect doesn't allow me to fly fast. The second problem is retreating blade stall, which actually is a form of dynamic stall, not a static stall. What is this thing? So what happens, I mean, once I go on the other side, because when I try to fly forward, my tip path plane has to go down. Okay. I mean, we have not analyzed the forward flight so much yet. So right now you have to take it a bit on faith. This will become more clear to you when we study the forward flight in more detail with BET and everything. So what happens, my tip path plane has to tilt like this, right? Only then my helicopter can go like this. Get my helicopter. So here is my helicopter. If I have to fly forward, my tip path plane has to, so the blade in the front should go down and blade in the back should go up. And the way helicopter dynamics works, if I want my blade to go down here and go up here, I must decrease my lift here. So I have to decrease my lift here so that this minimum lift here will cause minimum flapping here, because it's a second order system and my dynamics is such that the forcing and response delay is 90 degrees approximately. So I minimize my thrust here or lift here. So I decrease the angle of attack here. I get my blade to flap down here. If I increase my angle of attack and lift here, I get the blade to flap up here, that is behind the helicopter. So it will cause it to decrease in the front and increase at the back. Okay. So to achieve that, okay, here I end up getting high angles of attack. So now I mean on the retreating side, where I actually have a bad efficiency because there is reverse flow happening and all those things, I actually require very high angles of attack. And these high angles of attack will actually cause the flow to separate in a dynamic manner. And multiple cycles of separation and reattachment happens. And what comes out is called dynamic stall. We will not be looking into dynamic stall in this course. because of paucity of time, we have too many things to cover. So here, I mean, the Mach number is low subsonic, that's not a problem, but angle of attack is very, very high. So here I may end up getting stall, which will actually further increase my control loads and increase the vibration and not allow my helicopter to fly too fast. So these are the two critical limits which limits my forward flight speed turbine. Okay, remember this. Retreating blade stall and advancing blade compressibility effects. These are the two things. So even if I put a big engine, it's not going to help me. So how can I make my helicopter go way faster? What is the solution? We talked about that in our introductory lectures.
Smaller blades,
Sorry, what?
smaller radius of blades.
No. How can that happen? I mean, smaller blades will stall earlier if you're lifting same weight, right? That cannot be a solution. I have given you a helicopter. Now you have to make this helicopter go faster. You cannot change the blades. What can you do? You can add something. You cannot remove something. We did talk about that actually. Anybody remembers what is the trick to make a helicopter go faster? Which actually is resulting in a new kind of helicopter. That is the hint.
So VTOL.
Everything is VTOL. Helicopter is also VTOL.
I mean, sorry, sir. Like add wings and make
Compound
wings.
helicopters.
Okay.
You remember compound helicopters? Like I showed you this also. Raider, S-97 Raider. And then Racer, which Airbus is making. And in past, there were other compound helicopters such as Cheyenne. There was Rotodyne. What is the name? I forgot the name. Anyway, so and yes, of course, there was X2 and X3, which were both technology demonstrator helicopters. So that's the way. So what is the trick now? In compound, say for example, I mean, if you look at the Raider, which has coaxial rotors like this, exactly. I slow these rotors down. Okay, I slow them out, and by slowing them out, now if I have two rotors, then I can actually compensate for the additional thrust requirement. Okay, so I slow them by up to 80%. So what happens if I slow them out? My tip Mach number will drop by, so from 0.65, it will go to some smaller number, 80% of that, let's say. So that will now allow me to go faster. But the challenge is that if I still try to fly like a helicopter by tilting and everything, my helicopter pitching forward and going, I will have a lot of drag. And rotors will not be able to give all the thrust because I have slowed them down anyhow. So in Racer, in the Raider design, and also the larger version of the Raider is called Deviant. In these designs, I actually put a propeller at the back and get the forward propulsion separately. So now this propeller at the back will allow me to fly as fast as I want. And my rotors are slower now, but they will still be generating enough lift to support the weight. Other option is that, I mean, if in a conventional helicopter you have, I can put wings and propellers. So that gives you the Racer kind of concept, which Airbus is developing. And Sikorsky is developing this compound helicopter, which is also called advancing blade concept, ABC, where coaxial rotors are moving forward. So always both sides of the rotor actually are higher, advancing. I mean, both sides are advancing in some sense because of two pairs of rotors. So it actually takes care of your torque compensation requirement also, and it also helps you. So that is the idea. So you reduce the tip speed, and that will allow you to fly faster, but with auxiliary lifting and auxiliary propulsion devices. Okay, that is the idea. Now we look at a very interesting diagram which Leishman has in his book. That is this. And in this, let me explain what are the things. So this actually sort of gives you the the range of certain physical parameters which limit the design of a helicopter. So we saw already the limit in terms of your tip speed as well as forward speed. And that is this particular line which gives you the limit for compressibility or advancing blade compressibility requirements. For lower tip speed and higher velocities gives you another set of requirement which we call the requirement for retreating blade stall. So this is the retreating blade stall limit. On this side I have, so this is the limit of choice of tip speed versus forward speed. That is, how do you achieve forward speed with a given range of tip speeds and how you have to meet certain requirements. So these are two limits on that side. Now a third limit is there. Irrespective of my forward speed, there is a limit which actually is there because of the noise requirements. What happens for any rotary wing system, the noise that it generates is usually a fifth order function of the tip speed. So if I decrease my tip speed by even small values, I typically end up reducing noise significantly. So therefore the tip speed actually limit also comes. I cannot go beyond this because my noise may be too much. And at the bottom side, how low can I go? That is, what is the lowest tip speed I can choose? I mean, if I can go with very low values, I mean, I can always fly faster and so on. But then on the lower side, there is another further limit for auto rotation limit. Why? Because if my omega r is too low, the stored kinetic energy in the rotor blades at the time of engine failure, tail rotor failure, when you have to enter auto rotation, you may not have enough kinetic energy stored in the blades to allow you to go from that sudden unpowered state to the regular auto rotation condition where you start extracting energy from the air to some extent and maintain your rotor speed and rotor RPM without requiring engine power. So that's how these four limits are there. And within these boundaries of these four limits, one has to design the entire rotor for any helicopter, conventional helicopter. I'm not talking about compound because there, I mean, you are changing your tip speed and other things. So you can see if I want to design the fastest helicopter, I have to choose it somewhere here carefully, where I have best possible advancing blade compressibility and also best possible retreating blade stall, and I can achieve the highest possible speed. So this is now sort of like a design map regarding what kind of tip speeds you can select and what kind of forward speeds you would be able to achieve for the helicopter being designed. So now I'll have a couple of more comments regarding some remaining things, such as what is the operating ceiling. So for helicopters, the ceiling is defined in slightly different manner than for an airplane. For airplane, you talk about absolute ceiling and a service ceiling. So service ceiling is the maximum altitude where you can fly your airplane, where you can achieve a rate of climb of 100 feet per minute. That is 100 feet per minute. Okay, that is the requirement for service ceiling. Now, absolute ceiling is where you have zero climb rate. That is, climb rate is absolutely zero. But it's a theoretical idea. You cannot actually ever reach absolute ceiling for any aerial wave. All you can reach is service ceiling. But now for helicopters, what happens that, I mean, the hovering is a very critical parameter. So everybody wants to know that up to what heights can you actually do hovering flight? Because I can do forward flight at even higher altitude, but I may not be able to hover. Why? Why can a helicopter do forward flight but cannot do hover at a given altitude? What could be the reason?
Hovering power is more than forward flight
Exactly.
power.
So, exactly. So hovering power is often more than my forward speed power, right? Forward flight power. I mean, of course, beyond a point, it can again go beyond that, but typically it would be lower than the hovering power. So therefore, it is important to define heights where I can actually do hovering flight also. So for helicopters, we often talk about ceiling in terms of IGE and OGE. So they say hover out of ground effect ceiling and hover in ground effect ceiling. What is this out of ground effect and in ground effect business? So if my rotor is very, very close to a ground surface, then what happens that the air which is being pushed by the rotor, the downwards, will hit the ground and it gets recirculated and re-enters into the rotor again. So this actually creates some kind of air cushion at the bottom, and it actually minimizes the power required for the rotor to some extent. It's the same kind of thing which is also observed in airplanes, where when they come to take off and land, in takeoff and landing time, the wing lift requirement actually, or wing power requirement decreases, and you end up getting slightly higher lift for your wing when it is close to the ground.
Skin
This is
effect,
what-
sir.
What?
Skin effect.
No. What is skin effect?
Ground effect. Ground effect, sir.
Ground
Sorry,
effect, yes. That's what I'm coming to. So this is called ground effect. Okay, when you're close to the ground, and for rotors, it is like if you're flying at a height which is less than or equal to the 1.5 times of your rotor diameter. The typical thumb rule: 1.5 times the rotor. If you are closer than, if your height is any less than 1.5 D. D is the diameter of the rotor, or 3 times radius, one can say. I hope I'm remembering this number right, but I think that's what it is. If you're any closer than this, then you are actually operating in ground effect. And if you're even closer, if you're say at only half 0.5 D or some such small number, you will see strong ground effect. And you will see that your power requirements actually come down and you will be able to hover. So when a helicopter takes off, it can very easily keep hovering near the ground without consuming much power. So that is called hover in ground effect. So people actually, for helicopters, they find this out, that what is the power required in ground effect. And then they also find out what is the power required for out of ground effect, so that they can determine what altitude you can actually hover without requiring the ground below you. Why is it important? HOG, HIG, can anybody think of a scenario where this HIG could be useful for a helicopter pilot to do a particular operation?
Rescue.
Sea areas or flooded areas.
No, not at all in sea. I mean, sea means you are on ground level already. So you are not so worried about your power. Rescue is just correct, but not from sea areas. Because this becomes critical when you are reaching to the limits of your power available. Where will you reach the limits of your power available? What kind of places? What kind of areas?
Mountainous.
Mountain areas, exactly. So what happens? I mean, you imagine, I mean, okay, there is a cliff like this. Okay, and there is a person here who needs to be rescued. So helicopter comes and lands here. So because helicopter came in doing forward flight, right? So it can come here and do a nice touchdown. Now this guy is included in the thing, he has been rescued. But now, I mean, he has come, helicopter has come to such a high altitude, it cannot actually hover and go up and climb and do forward flight. So what the guy will do? He will do hover in ground effect. He will keep hovering here and start gaining some forward speed, and then do a slow dive and gain further speed, and then be able to do normal forward flight. So this is the scenario, the kind of place like when they're delivering packages in Siachen. Siachen is when you are flying at 18,000 feet, 20,000 feet kind of altitudes. So there what happens, I mean, you are actually operating at the limit of your power. So I was once talking to a pilot who does this kind of operation. So he was saying sometimes when they're trying to deliver this cargo and they are going to land there or something, they find that, okay, they cannot do a right turn. They can only do a left turn. Why? Because they have reached the limits of their tail rotor control movement. So my tail rotor's collective is at maximum value. So I can only reduce my collective. I cannot increase the collective any further. Or it could be power limit also. So that is the kind of challenging environment they actually operate in. So in such scenarios, being able to hover in-ground effect is very, very useful. He actually showed me a particular video where they actually took off exactly like that. Okay, so there was a cliff where you go and land and deliver the cargo here. And then when he is to return, actually, he just hovers, goes, and then he dives. And then he enters forward flight and comes down. Okay, so that is the deal with IG and OG. So people often define ceilings for helicopters in HOG and HIG. And of course, you can also define the service ceiling the way you do for a fixed wing airplane. But people are more interested in about this IG and OG ceilings. Okay. So just for your information, I will not derive anything for this. All right,
Sir, can you repeat OG part once again?
Out of ground effect. So the moment your height is beyond 1.5D, then you are out of ground effect. Then you are like normal hovering. Okay, what we have studied all along.
Okay, okay.
So OG is your normal condition. Only when you are close to the ground below this height, then you are in IG condition. Okay. All right. So I think that is all for our syllabus for the coming exam. Okay. We'll start beyond this in the next class. I'll also give you a homework assignment after this, which will be based on the previous work because we are already there for the exam. So I will not give you any homework assignment, but I've given you the example test paper, which you can practice with. So if anybody has any questions regarding exam or any other matter, any doubts regarding whatever we have covered so far, I'll be happy to answer.
Sir, we can use calculator, right, in exam?
Yeah, of course you can use calculator. Yes, you are an engineer. You are not undergraduate student, right? Or even a high school student rather, not even undergraduate, high school student. You are an engineer. You cannot live without calculators.
Sir, will calculator app?
Yeah,
okay?
of course. No problem with calculator app. But absolutely no cheating. If you have any question, any query, any doubt, you will ask me, not anybody else. And you should have cameras showing what you are doing clearly. I'll share the Zoom links before the exams. Okay. And be aware that, I mean, last time when people were caught doing cheating and all, they were all failed. So don't indulge in any such thing. It will not yield you anything good. It is neither morally correct, nor it is actually correct for your career, correct for your any aspect. So keep this in mind, not just for my course, for all other courses which you guys are doing. It doesn't help anyone. Right? So fine. So anything else? Any other question?
Sir, while you were discussing about dynamic stalling, you said something about a time delay response. Can you again at least say something about it?
Sure. So dynamic stall, what happens is I have any airfoil, any kind of thing. So nothing. So fine. We'll assume this is airfoil. Fine. My phone is airfoil. So in dynamic stall happens only in scenarios where your airfoil actually or your wing is actually doing this kind of repeated motion, and that's what happens for helicopters. In helicopters, we are always pitching and plunging, right? My blades, once I give cyclic input, my blade will always be doing some sinusoidal motion. And if you remember the video we saw of the blade of a helicopter in forward flight, we saw it was actually doing this kind of oscillatory motion and also doing this kind of pitching motion and everything. So normally when I keep increasing my angle of attack in a static scenario, I reach a point where my pressure gradient over the top surface would increase so much that the flow will separate and I'll get a static stall. But when I'm moving so fast, the flow separation and everything actually depends on how fast I'm moving, because it will depend on the history of at what state I was or my airfoil or wing was in the previous time step or previous condition, previous situation. So all those actually play a role. So here also what happens, I mean, when I actually start flying, so what happens with helicopters is that because to go at higher speeds with high weight condition or even at lower speeds at higher thrust condition, my blades may be operating at very high angles of attack. I mean, first of all, they operate with very high pitch angle. The pitch angle, if you look at the peak to peak variation, how it is varying the sine wave amplitude, it will be as high as 20-25 degrees. Okay. I mean, I don't know if I have my presentation handy. From my PhD defense, I could have shown you exactly how high they become. Let me just give me one moment. I'll just check it if I have something. Okay, I got my PhD students presentation. Maybe it has something. Let's see. I'll just quickly check it. I mean, I was hoping to find my own PhD defense presentation. I don't know where. Maybe I have saved it somewhere else. Yep, I think I got it. Yeah, this is the graph I was looking for. So let me share my screen. This particular. Yeah. You can see the presentation, the PowerPoint.
Yes, sir.
So you see, this is actually a real condition for a dynamic stall scenario where your angle of attack is going to 20 degrees. Okay. More than 20 degrees. This is angle of attack, not pitch angle. Pitch angle will be actually much higher than this. And if you see this dashed line, black dashed line, which I am trying to follow, this is the static stall limit for the airfoil, which is there on that particular. So this actually is a scenario for Black Hawk helicopter for a particular maneuver. So this is SC 1095 R8. Actually, there's a typo here. So with this 1095 R8, there is a stall limit, and you can see this airfoil is actually going way beyond the static stall limit for this airfoil. So this is called deep stall condition. So what happens when the blade section goes in such kind of deep stall scenario? The adverse pressure gradient will actually cause the flow to separate. So flow will separate eventually, and the flow separation will actually be triggered by this dynamic separation bubble. So in the leading edge, so if I say this is my leading edge, so leading edge, there will be a bubble formed, yes, separation bubble. This bubble will then travel along the chord of the blade. Okay. So it will keep traveling along this direction, and while it keeps traveling, you actually get a dramatic benefit. What happens? Your lift actually keeps increasing because this is a suction bubble. So if you plot the CP on the top, you'll see it will create higher peak in suction. So your lift actually keeps increasing, and while it is traveling, your lift will keep on building. So I will give you an example by drawing something here. Oops, sorry. Yeah. So are you still able to see the diagram I've drawn?
Sir, only the axis X and Y axis.
Right. That's all I've drawn. Yes.
Okay. Okay. Sir.
So now on this, normally what happens? I mean, my lift will go and decrease like this, right? But with dynamic stall now, because of this laminar separation bubble, my lift will actually continue to build up further. And then when this separation bubble leaves the airfoil, so it will leave the trailing edge, it will go from the trailing edge from here. Okay. At this juncture, the lift will suddenly drop like this. Okay. There will be a dramatic drop. And at the same point, we also experience a dramatic drop in my pitching moment. So if my pitching moment is there, the pitching moment will also decrease with a very spiky kind of sharp peak. I can show you a graph of that here. So you see this black thing. Okay, this black thing is actually actual dynamic stall in the pitching moment. So there is a stall in the lift, and there is a stall in the pitching moment. So this, because this bubble has now left, so it suddenly, it's like this. I mean, see, you have imagine a scenario where you have a seesaw or something, okay, and you have some high load on this, and this high load goes away, right? I mean, both sides you have equal loads, whatever that load is, equal loads, and I drop this one load, suddenly it will see this jerky behavior, right? The same thing the airfoil experiences. This vortex leaves, and you see a dramatic spiky drop in the pitching moment. So there is a nose down pitching moment. And the lift also decreases after that, but lift drop is not very sharp like the pitching moment. So this is what happens in the dynamic stall. Now, this happens, I mean, when the angle of attack is increasing, and after a point it will start decreasing. So what happens once it starts decreasing, the flow will reattach now. Now, at a later point, my angle of attack may increase again. And in that case, the flow may separate again. So you actually end up getting multiple stall cycles on this side. Like you see, one stall, two stall. There are two stall strong peaks here in pitching moment. So that is the whole deal with the dynamic stall or unsteady aerodynamics here. So these are all studied in part of unsteady aerodynamics, how this mechanism of this leading edge vortex, how it is generated and how it actually travels. So this whole thing actually is caused with a delay. So your stall is delayed because this guy is traveling. So the time it takes for the vortex to travel along the chord of the blade is actually a function of the frequency at which you are oscillating and other parameters also. So this leading edge suppression bubble or suppression vortex causes delay in your stall by allowing you to extract more lift, but then it comes at a cost that you actually end up getting very high spiky pitching moment, which tries to pitch down your nose of the blade or the leading edge of the blade. And this actually excites different kind of dynamic motion in the blade, which further combines and allows you to or causes more stalls in this side. So it's a slightly complicated answer, but that is all I can give you as a summary and overview without actually having to teach the whole thing from ground up.
Yes, sir. Thank you, sir.
Anything else? So even when there is no dynamic stall, like such significant dynamic stall, you may still have unsteady effects. Because and we'll see very briefly, we'll see some unsteady aerodynamics towards the end of this course when we talk about aeroelasticity and when we try to look at the instability that the rotor actually encounters. Okay. So fine then, I'll stop now. Anybody else has anything else? Any other comment, concerns?
Sir, kindly upload this week's lecture, sir.
Yes, so I have already uploaded the lecture from Tuesday, and remaining lectures I'll upload by tomorrow morning. By tomorrow morning, both other lectures will be uploaded. Okay.
Thank you, sir.